Another thing that I worry about is that the notion of isotopy is, as you said, not sufficiently well defined. That the very earliest articles that I could find about isotopy don't limit the types of mappings to be multiplicative mappings. You know, the mappings, as you said, I think just briefly, that we can look at the isotopy as a kind of algebra map, and that when we look perhaps backwards along that map, then we see some different mathematical structures that have some different properties and perhaps useful properties, right, under that particular mapping. But the mapping is preserving certain properties, algebraic properties, and it's the original reasons that I saw in algebra for introducing the idea of isotopy was a kind of generalization of isomorphism, and so that it was considered, especially in the case of non-associative algebras, that the notion of isomorphism was not sort of sufficient.
Yeah.
And so people like Albert introduced the notion of isotopy as being a way of overcoming this, right? And being able to study algebras abstractly without having to resort to the representation of the algebra.
Yeah, but here the idea of isotopy, I think that is related first with the idea of extension that was not clarified, because extensions means process. No? Extension means process. And then when the idea of extension is related to ISO number, I think that this is not correct use the term of extension there. Before, we need to include the idea of process. I am thinking in the idea of process in the way that Professor Rosiewicz used to use for vectors or...
Yeah, so you mean abstractly speaking, in the algebra, we need to introduce derivations. Right?
Yes.
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 And then once we have then we can discuss extension.
Then we can discuss extension. And after the idea of isotropy, I better I think that it's better to speak about non-isotropy, because the use of different kinds of units are related with non-isotropy. I am thinking in the idea of continuum mechanics, for example. No?
Yes.
The formation is not the same in all directions, because the structure of the material introduce condition for the formation. And in the same way, I think that the introduction of different kind of units for the space is related with a non-isotropy of the space.
I could give maybe a counter example of that, and that is what Sobchak was doing with geometric algebra and what he called isogeometric algebra. In that case, the relationship between the units and something like extension, at least volume, right? In the case of Clifford algebra, it's clear that the iso units are related to the pseudoscalar, to the basis of the pseudoscalar.
Yes.
You know, and I'm not sure. Like, and that happens there in geometric algebra without any, like, without discussing calculus yet, without discussing any notion of derivation. So I'm not sure. Maybe for that reason, I'm not sure what Garrett Sobchak is doing is necessarily that closely related to isopody in the sense that Santilli was hoping to use, what he wanted to use in physics. Like I don't know. I still remain uncertain, right?
Yes. But the idea of Santilli is, I think that is more properly related with extension. I think that this is the principal idea, and then we need the derivation for speak about the extension. And then if the extension is not the same in all direction, then I think that we fall inside the problem of non-isotropy.
Well, here in geometric algebra, there is a clear notion of the well, how should I put it? The what's the right word? The degree or whatever. So if we talk about scalar values, they are of degree 0, and if we talk about vectors, they're degree 1, and if bivectors are degree 2, and this distinction between the grade is I'm not exactly sure. Like this distinction between, say, a vector and a bivector has something to do with extension in an abstract sort of way, right? So that we think of bivectors as being related to areas, of oriented areas, right?
Yes.
And so we can't really think of points as having areas, right? So if we describe something that requires that we use a bivector component, then we're sort of no longer physically speaking about something that is limited to being just a point. At least we're talking about something that has an orientation, something that has some sense of shape, so the grade somehow relates to shape in some general sense. And so what I see happening in Sobchak's isogeometric algebra is a kind of mixing of the basis elements, but mixing the basis elements between different grades. It reminds me a lot of what another colleague of Wilshevich's was promoting, I forget his name right now. Schmiel, Bernard Schmiel. Um, I, maybe I'm not pronouncing his name correctly. He's from Austria. Um, he he shared some experience with Loshevich because he also spent some time in jail. Um, and but he was often contributing to Clifford algebra, um, especially at the meetings that I attended. Bernard Schmiel would give a somewhat sort of philosophical paper about the applications of Clifford algebra. Um, and he most recently, I think in the last year, wrote a book about the idea of using Clifford algebra to understand space-time, the structure of space-time. And it's not so different in some ways, but also a little more metaphysical than what Sobchak was doing or in his work. But the main thing that Schmiel talks about is how in Clifford algebra you can see various algebraic structures in the mixing of the grades, so that it, this was exploited, for example, by what's his name, Baylis, William Baylis, and he presented the notion of paravectors as like the combination of a scalar part and a vector part um, as a sub-algebra of geometric algebra, and pair of vectors form a kind of model of Minkowski space. But from the geometric algebra point of view, they are a combination of a scalar and a vector in the Clifford algebra of three-dimensional Clifford algebra. But the pair of vectors actually are a model of four-dimensional space-time. And I've always been a little bit curious how that mixing of the bases somehow changes the algebra in interesting ways. And Schmiel was taking that much further and saying, well, how this happens in general in Clifford algebra, and how from Clifford algebra you can get almost all of the interesting small algebraic structures, all the spin groups and all. Essentially, I think he wanted to claim even that you could basically represent the symmetries of the standard model in physics through this kind of view of taking Clifford algebra as the basis for all of that, provided that you are willing to understand that some of the objects that you're talking about are mixing grades, like they compose. They're still elements of a Clifford algebra, but they're selective subparts of that algebra that have different structures because they're structures. Even though they're a subpart of some larger structure, this subpart has a particular algebraic structure that's relevant to different aspects of physics. And this idea of a paravector as being a subset of a three-dimensional geometric algebra, but still representing the structure of Minkowski space, of space-time, is kind of appealing and convincing to me in some ways that something like this is going on. So in Sobchak's at least draft views of what you could get when you're doing isogeometric algebra, I almost see this as a kind of more formal presentation of the same ideas that Bernard Schmiel was promoting. That we can see a lot more in Clifford algebra by allowing for this kind of isotopy. And that we don't give up the structure of the geometric algebra. It's still present, but we're just looking at it from different angles, from different perspectives, and particularly those perspectives that mix grades.
But in the idea of Clifford algebra in the thinking about the units in the it is used to think about the norm the same in all directions. The norm is the same in all the
Not necessarily, I think, because the Clifford algebra can be written with an arbitrary metric. You only need a scalar product.
yes.
But that scalar product doesn't necessarily have to be isotropic. It still has the structure of the Clifford algebra, provided
Yes.
that you have
yes.
any scalar product you like
Yes.
for it.
Only we need to select scalar product or a metric for that space, and then of course we have the complete algebra, Clifford.
This was something that I think Ilshevich was from many years ago. He felt that Clifford algebra was sort of not necessary, right? Because you could start from Grassmann and you could do everything that you wanted with Grassmann, and Clifford algebra arises only because you're forced to choose a metric tensor. So once you choose the metric tensor, then everything else in Clifford algebra arises from the Grassmann structure, especially if you pay attention to the fact that the Grassmann structure is two branches, is a dual algebra that has both bivectors and two forms, has both vectors and forms. And it's almost everything that you want to do in geometry that I can think of can be expressed in terms of these two dual algebras, in terms of the vectors and forms. And provided that you introduce this metric tensor that gives you the isomorphism between the vectors and the forms. So this isomorphism is what Ilshevich insisted was the core of what makes geometry. So if you didn't have this isomorphism, then it's clear that you don't have geometry, that you just have the algebraic structure of Grassmann algebra. But when you introduce the isomorphism between the two parts of the Grassmann algebra, then from this you construct Clifford algebra. And from Clifford algebra, it's clear that you have geometry. Right? And you can then talk about things like isotopy, like what it means to be in scaled differently in different directions and so forth. You can't really say anything about it at the level of just of Grassmann algebra alone. But if sometimes I worry that the people who are thinking about Clifford algebra sort of have forgotten that the origin, the origin of how Clifford algebra developed, and especially its relationship to Grassmann algebra, which, I mean, of course, everybody's sort of aware, but it's not really exploited.
yes. But I have here a problem with this concept because surely you have read the paper of Frolinger Nijenhuis about the multi-vector algebra.
Yeah.
And this approach is complementary to the scalar forms. Then with the multivector algebra, we can build one graded vector algebra, no? Graded vector algebra. And we have at the same time the scalar algebra or scalar forms algebra. No? Then we have the duals algebras that completes all the but then Clifford algebra, we can think that is in the multigrade vector algebra. I don't know if I am in the correct way, but I understand that this is
I think so, but for me, I think it has to do with the scalar product, because in Grassmann algebra alone, or even in multi-vector algebra alone, there is no obvious definition of scalar product. But so in a sense, we have vectors, but we don't have any way of assigning the length to the vector.
But if you multiply the vector with the scalar form.
Yes, but the scalar form should come from the isomorphism, right? So that we should map the vector into its form and then apply the form to the vector. And this is the scalar product, right? I mean, unless you mean to fix only one scalar form.
Only because
like trace. So for example, a trace is the example of a form, right?
Okay.
Kind of a natural occurring form is a trace, right?
Yes.
It means that we can take a vector and get its trace and get a scalar from this, right? So we think of the trace operator as being a one form.
Yes.
But it's a distinguished one form of some kind. It's kind of a naturally occurring one form, provided that we assume something about the algebra, that it's a trace exists, for example.
Because then here we arrive to the Frobenius problem, not? Then we can, if we have vectors forms and scalar forms, then we can associate this with operation of creation and annihilation. No?
Mm-hmm.
And then the product of this give to us scalars.
Yes, yes. So you create and then you annihilate, but the result is a scalar. Yes.
Yes, yes. And then one way is, for example, taking the trace of, but we can take the determinant of this representation, no? Or take the cofactors of this.
I'm not sure. How do you define the determinant if you have, if the only thing you have are vectors? What do you, vectors and bivectors, graded vectors, how do you define what is determinant?
Because if we go to a higher degree of vectors, if we go to multi-vectors, then we can associate different kind of I wanted to use the word metric because in fact we are looking about invariants of in the systems, and one invariant is the trace, and the other invariant is the determinant, and other invariants are the cofactors of this. And then when we multiply one multi-vector with one multiform, we can get this different kind of invariants that are different scalar associated to the system.
That's interesting. I'm not really sure yet how to conceive of the determinant. I mean, of course, I understand that the Grassmann product is related to the determinant in some general way. I have to think about that. But no, I think you make a good point that maybe there is. For some reason, I don't like or don't want to think of the determinant as being a form. You know, so I think of the trace as being a form.
Okay, but it's a form of the degree 1. No? But then we can get the multiforms in this way. I think that I am going to try to organize this idea because I was trying to use in the idea of interaction, because for me interaction is the product of one multivector with one multiform. And then we can have different kind of products here that are speaking about different kinds of.
Well, let me try to make an analogy with physics that if we have a material body, we can, as Olszewicz does, we can clearly define a process. Like, and the process is associated with what we would mathematically refer to as a vector. Right?
Yeah.
But we haven't quite done enough, right? So what happens usually is that we assume that there is not just vectors, but vectors are part of a space that has the kind of structure of geometry. And so then we can say we have something like a scalar product. Uh, um, but if we start just with saying we have a material body and associated with the material body is a vector, then we still don't have any forms, right? But perhaps in Shevich's sort of metaphysics, he would say that it isn't sufficient that you have just the process. The process also has to have a clock, right? So the clock is the form that's associated with the material body. But it's not the same thing as the time-like vector that's associated with the material body. So that this clock, so the vector is associated with time, with the progression of the material body through
Yes.
time. But the clock is how you measure this time. But the idea I think he had was that the clock, being a form, like is another piece of information about material bodies. You know, so in the conventional approach to relativity, it's done differently. That it's assumed that you have vectors and you have a metric, and from the metric you can get. From the metric is what you use to measure time, because you take the vector and you take the corresponding form associated to that vector by the metric, by the isomorphism between vectors and forms. And then having done that, then you measure time by the ambient geometry. So it makes the concept of time outside of the material body. It makes it somehow time is a property of the space, of the structure of space. But I think what you were saying with interaction is at a deeper level, so that somehow, and I see that sort of as being compatible with what Roshevich was saying, is that this the structure of vectors and forms is prior to the notion of space, is prior even to the notion of geometry. But we can still have the notion of interaction, but we need to have at least the willingness to say that associated with every material object is not just the property of viewing that object as a process, but also we must view this object as being, in another context, I know another author has referred to this as it being the system, or the action, maybe is better, is to say that we have both the process and the action of the material body. And together, the process and the action form the system that is the material body in abstract form.
Yes,
and the word action is important because it's links to dynamics, right? So the action is what is minimized when you deal with Lagrangian Euler-Lagrange representation of dynamics. But it's not the velocity. It's the clock part. The clock part of the object that gives rise to the dynamics.
Yes, about the relation of this with the idea of time, I have not thought too much about this, but about interaction, interaction, we have either two kind of mathematical objects that are related in the interaction. For example, we have vectors and forms, and then the product of vector and forms give to us one scalar that maybe can be energy or something like this.
Yes.
But there are many types of properties in a natural body that are more complex. For example, spin. Spin is more complex than maybe we can think about this in terms of b vectors, by vectors. And then
I have some ideas about that. As soon as you say spin, the first thing that comes to mind is that we are interested in trivector-based isometries, right? That we need to know how to map space onto itself, but not just by reflections, but by the action of a trivector.
The action of a trivector.
And it's not just rotation. It's the distinction that that we cannot that in 4 dimensions at least, that that there is such a thing as simple bivectors and non-simple bivectors. And so the simple bivectors can be represented as just the Gaussian product of vectors. But the non-simple bivectors in more than 3 dimensions, the non-simple bivectors don't come from products of vectors. These trivectors come from, or these bivectors come from the contraction of a trivector. So the contraction of the trivector gives you a bivector which is not represented by as a simple product of vectors.
Okay, but
so
now
the spin comes from that structure, right? From that part of a bivector which is not simple.
okay, but then if I understand, we can go to a bivector with the product of 2 vectors, but we can go to a bivector by the contraction of a 3 vector.
Correct. Yes. And so spin looks like rotation because it's related to a certain bivector. But spin is the part of the bivector that doesn't come from the product of just 2 vectors. It's like a kind of rotation, right? So you can.
When I brings here the idea, the example of spin, I was not thinking in spin about rotations. No. About one object that is more complex than a vector. Then I say, for example,
you mean like a spinner in that sense, right? In quantum mechanics, in the Dirac case, for example, we think of the wave function as a spinner equation.
Yes, but maybe because here there is a big problem with when we go to other properties of the matter that cannot be described by vectors. And then I think that we had to look about the higher degree of mathematical objects that describe this in accurate way. And the idea,
your idea, I agree, right? And I just wanted to relate it to what I said earlier about mixing grades, right? Because, for example, spinors can be viewed as a subalgebra of Clifford algebra, a particular subalgebra that is a mixture of two grades.
yes, yes, but I think that, for example, in the I am going to back a little here, and I go back to the idea of energy. And in the idea of energy, if we think about the electromagnetic field energy, we need, for build the energy, more complex objects. Because energy is the product of one in the general way, what we think about the interaction in materials, interaction in material, then we need to build energy like tensor products. Then the description of the properties of the systems are not more vectors, are not vectors. Necessarily, we need to include here tensors, and then
or at least the bivectors, right?
At least bivector. And
yeah, I hesitate to say tensor because I don't want to go outside, right?
See, and at least the added product, for example, the added product. And this is this kind of operation is equivalent to a contraction between multivectors and multiforms. Is equivalent to this. And in this idea, maybe we can describe interaction in a more general way by products of multivectors and multiforms or higher degree. And then in this way, I think that the two parts of these products are fundamental. Fundamental.
So would you say that all contractions produce the forms? You know, so I would say, I was saying, well, you know, I understand that a form arises as a trace of something, right? But well, we can think of contraction as a kind of generalization of trace.
Yes, yes, this is the idea. This
and
is
so
the
contraction belongs to the form part of the algebra.
yeah. Yeah. And this can build from going from one degree to the to another byproducts of creation and annihilation, but we can use more higher products of this, and then
Yes.
going to the scalar.
In Oshevich's draft lecture notes, most recent ones, I think in the last couple of years, he introduced this notion of creation and annihilation as being related to the Grassmann product and the insertion operator, right? Or contraction, basically.
Contraction, yes.
Yeah, so contraction, of course, is annihilation. And this structure of just those two operations of creation and annihilation, or well, instead of annihilation, he used the word evaluation.
Yes.
So we have creation and evaluation. I think annihilation was a bit distracting. Right? It was like it didn't have not quite the correct intuition, right? Because it's you create something, but you don't annihilate it. You just evaluate it, right?
Yes, this is correct. Because this is part of one Cartan lem.
Mm-hmm. Yes.
And this is evaluation. This is evaluation. Yes.
Mm-hmm.
And in this Cartan lem is used for higher degree of form.
Yes.
And multivectors. Yes. Mm-hmm.
But I like this. Your view on interaction. I like to understand it a bit better, because especially where the forms arise from. So that it's like when we say that we have, say, one material object interacting with another, it's easy to think of these material objects as processes, but we don't have enough information yet to talk about interaction. If all we know are the processes, right? We need to have some understanding of how one process affects another. But the only way that we can have this action of one process on another is not from the aspect of this object as a process, but rather some other part of the object, some other part of the object that it has to be able to observe, right? In order, it has to be able to see, right? And seeing as something else is not the same thing as just existing, right? It's not.
Yeah. But the other part is the property of matter.
So you accept the idea that if we describe matter, we have to describe at least two aspects, right?
Yes, at least two aspects, and one can relate one aspect with multivectors and the other aspect with multiform.
Mm-hmm.
And
then I like the idea that we accept that this is true of material objects in abstract, right? And that we don't expect that this relationship comes from geometry. So in the conventional relativity, we insist that the other aspect comes from the metric, basically. That when one object measures another object, this involves a scalar product in some way or another, and the scalar product involves this metric isomorphism. Um, and so it's not the property of the object that measures the other object, but rather the property of space. This object, the fact that this object is in some geometric space, then as long as we accept that, then we can naturally associate with that object, with the process, some corresponding form. That the form comes from the application of the metric to the other object. But I like your idea better, that, and I'm not, and Shevich was resistant in the discussions I had with him about emails, in the emails back and forth and so forth. Early on my discussions with him, he was quite adamant that no, we don't want metric, like eliminate metric, stop metric. But then towards the latter part of our discussions, he resisted the idea to introduce, instead of metric, to introduce another aspect of material body, because he was very much focused on the idea that the material body has to be represented by a time-like vector in the Minkowski, sort of view, that the most abstract representation of the material body would be just the material body as a process. So, but always, when you say vector, you always should insist that it's in the most abstract, right? So that it's the vector as a derivation of some algebra, and that this derivation is a representation of change in some way. So,
Yes.
So fundamentally, a material object is something that changes in a very specific way, right?
Yes.
In some ways, it changes in such a way that it remains the same. It's kind of a strange way to say, but just the continuation of that object in time is what we mean by the process associated with that object.
Yes.
Okay?
Yes.
So
Yeah, and then here we arrive to the problem of what is space and what is time. Because if we started with the idea of interaction, we have not space and time
not yet. Right?
Not yet.
Mm-hmm.
And only when we have interaction, this is related with change, with one change in the system. And this change in the system is related with time, and another change are related with the space. No? And in this way, we are changing the approach, because there are not events in space-time, but there are space-time in the event, inside the events, and this make one subjective idea in the concept of space and time, because one can decide make another kind of representation of the event.
Well, yes, this in Bashevich's last paper, and in some of the lecture notes also, he describes this algebra map that so he describes both derivation of the algebra and the algebra map, and the derivation of the on an algebra produces the time-like part, right?
Yes.
And the algebra map is what preserves the space-like part, right?
Yes. Mhm.
So it's these two mappings that make this distinction. The fact.
Yes, but then we can explore about different kind of derivation. For example, more higher degree derivations and
Or we
relate.
can you mean extend them
Yes,
over the Grassmann algebra, right?
yes, 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 yes. And then we can split the scalar in different ways.
Yes.
In different ways. Yes.
Yeah. So but you go further with this interaction theory. I think it's you go a little bit further because you have this notion of how you describe the interaction. It has to be in terms of a form, right? It has to be, it's the action of the form on the process of the external process. So just to use simple terms, like to say that we have an observer as a material body, and this material body is a process, but because it's an observer, it also has a clock. Right? So the clock is how this observer measures time. So when the observer observes an external material body, it does so using its own clock. So it's like the form is applied to the vector to produce this scalar, right? That is making a measurement. Is the observer making a measurement of some external event, I guess.
In Affir's approach, my idea is that we are speaking about natural laws, natural laws, not the observation of one observer. And if we speak about the interaction, then interaction like an event subject to natural laws, then we are described with these two parts. One part is related with the material properties, and the other is related with the interaction field. And the product of these two are the registration of the event. But then if we expand this to more objects interaction to design to inside the system, one of them can be one observer. And the observer is looking the interaction of the others. The others.
Yes, I think I see what you mean. The word observer is not appropriate for what I wanted to say. You say interaction, and I want to say something like, before we can. Well, let me make one other example. Is the notion of absolute acceleration versus the relative acceleration. So it's a problem in relativity to understand what is acceleration, because it seems that acceleration is absolute property of the object, of a material body. We can say that there is a difference between an object which is accelerated in itself, like without any reference to other objects, versus the apparent acceleration one would observe by an external object would observe, right? By its due to its own motion. In which case, this external observer measures an apparent acceleration, but nothing has changed in the object. Right? But there, so that could be like relative acceleration. But there's some kind of notion of absolute acceleration as well, that it comes from inertia, basically.
Yeah.
That there is a property. Now, why do I want to say this is related? Because this property, I'm quite sure this property of acceleration can be related to the change of the clock. It's not. So it's not the change of velocity that's important, because so it's not. What's important is that when you accelerate something, you're changing its clock. And so I want that interaction between bodies is expressed in terms of, say, something which affects the clock of another body. So if we agree that two bodies, at least in abstract, have two properties, they have a property of being a process related to time, and they have the ability to interact due to the fact that they have this form, like they have this way of, and I don't want even to say measurement, but even before measurement, there is the notion of interaction. And so you want one body to be able to, through some action of some force, right? You want this action to be a change of some property of the object, of some external object. So you want to, the interaction must change something in its. I get lost.
No, because I think that I understand that if we have two bodies and they are interaction, the interaction in the first body, the body A, we say, is produced with body B, is produced by the presence of the body B in A. The presence of the body B changes the state of body A. And this change here is one manifestation of the presence of the body B, of the body B. Then here are the two parts that are within the interaction. One is the field produced with the body B that is modifying the properties of the body A. And this, since the viewpoints of formalization are maybe one multivector, and here is a multiform. And this is important because here there is the idea of the multivectors is the action in one point, and multiforms is the change in one extended object. Extended object.
So, okay, so now I use your language. So I say acceleration is the change of state of an object, right?
Okay.
It's not, we should not think that most abstract concept of acceleration leads to change in velocity. This is not correct, right? But rather it's a deeper thing that's happening, that when two things interact, as you say, so the presence of one body gives rise to the acceleration of the other body because it experiences some force. What you're interested in is how that body is changing its state. And that state is represented, at least from the point of view of special relativity, as its clock, right? So
okay.
The presence of the other body changes the clock of the first body, right? So,
yeah.
So this change of the clock is the same as what you meant by change of state.
Yes. Okay. Yeah.
And yeah, I think it's good. I like somehow to proceed with this, and this is exactly the kind of discussion I had with Shevich in the last few years, is to say, how do we go beyond this relativity? How do we go? And your ideas that, are you still there?
Yes. Yes.
Oh, okay. Yes, this idea that you have of interaction, I think, is definitely good. It's a step from just kinetics into dynamics, right? So it's a step towards the dynamics. So interaction is kind of like abstract dynamics. It's not just kinetics. It's not just how things move. So,
yes.
But you must be concerned with how things affect each other. So really, you're doing dynamics in the most abstract way. And this was a problem in Shevich's whole approach, is that he got to the point of completely understanding the kinetic part of relativity.
Yeah.
But as soon as he started to think about acceleration, it was a problem, because he didn't want to accept the notion that he needed to extend the notion of a material body beyond just knowing this vector that represents the material body as a process. But I think that was blocking progress, because he was willing to say, well, maybe we, in order to understand that a body is rotating, we need to have bivectors. Maybe to understand spin, we need trivectors, maybe. So he was willing to say, well, we basically need Clifford algebra, right? We need the language of multivectors, right? But with just this language alone, you don't have a language in which to describe interaction. And you can only talk about kinetics. You can only talk about how things move. You can talk about how things move relative to other things. So they can talk about relative rotation, this sort of thing. But you can't describe the notion of any sort of dynamical notion, any kind of, as you say, interaction. Because with the interaction, I'm sure now that you need to extend the notion of material body. And it's not enough to just to say that the material body is embedded in some ambient geometry, which is the usual solution. The usual solution is to say my material body exists in space, and space has curvature, etc. And so we can say how one material body affects another material body through the curvature of space, right? But we're doing that exactly at the, in a backward way, like so we're, I think what you wanted to say is more direct, is to say that the presence of a material body B has a gravitational interaction with body A, and has this interaction has nothing to do with the fact that both of these objects are in somehow in sense in space in some geometry. It doesn't, geometry is just part of the language we use to describe it, or might use to describe it. But even before we have geometry, we still have this notion of interaction, of how the presence of this one material body B has a gravitational interaction with A. We must be able to describe that interaction without any reference to the space in which they're located. But the only way we can do that is if the material body B has to have, or at least either B or A, maybe A. It's the presence of B that affects the state of A, right? Right? So B causes A to accelerate, that is, change its state, right? Because the A has these two different properties. One is what it is just because it exists. So B exists. So only thing we need to know about B is this vector part of it as a process, that it exists. But about A, we need to know something else. Other than that it exists, it changes its way of existing, its mode of existence. And so that the presence of B changes state is a very critical idea that you can only really express if you have some other aspect.
But for example, if we think about you say a gravitational interaction, maybe we can, in first place, we can think about only one dimension, because only the distance between the bodies are important. Then we will, with this.
Don't not too quickly, because when you say distance, I think you want to also include direction. So it's one dimension, but it's important that which direction. So
no, because we only need to think about the idea of approximation of and not it is not important how is those are
no, but I think maybe it is important, because we want to say that it's B that changes A, right? Like so this, now it might be true that in at least one dimension that but this might be a accident of the mathematics of one dimension, right? That we can equally say that when B is affecting A, that there is always a sense in which we can say the opposite, the dual relationship, that we can always say that A is also affecting B, but only in some kind of relative sense. But the important thing is that's why I wanted to distinguish that A has two properties, but B is the only property of B that's important is that it exists, that it's present. Because we want to think of B changing A. In order to have the dual,
but
that would mean we have to switch, right?
first, wait a moment. I need to connect this because maybe it's going to plug off.
Oh, okay, sure, no problem. I think the time is passing, and maybe
Yes.
we should say perhaps that it's time to say is enough discussion for today. But if you have some idea that you wish to conclude.
No, maybe only add one idea, that is that when I think in two bodies, only the body A get the presence of the body B,
Mhm.
and get the presence of the body B because body A change,
Yes,
because it changed. And then the difference between the two states in body A is one medition of the action of the body B.
so but still, do you agree that that the notion of distance is not quite sufficient for interaction, that because you want to know the distance between from A to B. You don't care about the distance of
No,
B to A.
but here I go to the idea of building the concept of a space, and then body A have a different state, and this different state is related with the distance where the body B is. In this way, and when another kind of interaction appears, for example, central body interaction, central force interaction, then central force interaction need to be vector. And the change in A are related with that characteristic of the interaction. And then body B thinks about two dimensions. In this way, I think that we can build the.
But body, yeah, but you, if you speak, and I think you said it's good. The body B thinks about this, right?
Yes.
But this is body B's picture of the interaction. But when we talked about the interaction at the beginning, we said that B affects A. So
yes.
So B is affecting A, right? So so we don't want that because B thinks about A, that B's state changes. Like so B doesn't start to move because gravitation because it thinks that A is present, right? But the other way, that B is present, so it changes the state of A. And nothing to do with thinking, nothing to do with the model of what's happening, but
No.
it's a physical absolute statement that B has an absolute effect on A.
Yes, but here the idea of thinking is a way of speaking about the change in A that is going to equilibrium again.
Mhm.
Then A is put out of equilibrium, and A go again to equilibrium.
Yes, I think so. Yes. So it's something like, to put it in the language that I was using, that the presence of B changes A's clock, and that puts A out of equilibrium. And when A returns to equilibrium, its velocity is different. It's the result of this being in a different state. And to put the state back into equilibrium is the acceleration of
Okay.
A.
Okay.
So the presence of B changes the state of A, and then A must react. Right? It must take as a process. The process will change because in order to keep the body in equilibrium. And this notion of equilibrium is exactly what happens in Euler-Lagrange, right? Like what's so important about this minimization? Like what for what reason can we get dynamics out of optimization? So A is acting like it wants to get back to equilibrium. It has to. So that's the only thing we have to say. And then, so as long as A acts to move towards equilibrium, then the dynamics comes from that. Even though dynamics is a relationship between two bodies, the action that follows from this interaction, the maybe reaction that it follows from the interaction, is what gives the dynamics. Yeah, I understand more now.
Yes. Yes. Okay. Okay.
Yeah, I hope you can continue. I hope you can continue to work on this abstract interaction idea.
Okay.
It's I think it's maybe difficult for people to understand, like that, like what, because they don't generally want to give up so much, right? They want to, they don't want to be, don't want to start from such fundamental levels. But there are some people who are discussing sort of pre-space, like the notions of what is in physics before we even have any geometry at all. Like in a sense, people are discussing how the concept of space-time might be emergent, emerges from something deeper that somehow, that in that deeper thing is somehow related to quantum mechanics. So we describe quantum mechanics without having to talk about geometry. But quantum mechanics makes it necessary to talk about, something like interaction.
Yes.
And that when we start with this interaction, then when we understand the interaction better, then we understand that the interaction between bodies is what gives rise to space and time. Right? So, but classical mechanics is the other way. It says Newtonian mechanics is we have space and time
Yes.
starting, right? And then we put the bodies into that, and we
Yes.
have classical dynamics. But your approach, as you said, is the other way around. That we have, first of all, the interaction, and then the interaction gives rise to the concept of space.
The concept, the idea of
but the space and time is not the necessary. It's not. It's only a tool that we use to describe the interaction.
Yes.
In a more convenient way, perhaps. Or
yes.
Or as you said, that you think it's what B is thinking about. Right? It's the model that B creates because of the interactions.
And because the idea is when we consider the complexity of the interaction, then this is related with space and time. And maybe sometimes not enough with two bodies. Maybe we need three bodies,
yeah,
or more, in the way we can wield all the and there is a general idea, for example, in the Euler angles, we start with the idea that we only need 4 points for describe all the movement of this body, because he is thinking in rigid body.
Yes.
And then it is enough with 4 points. But with 4 points, with all the complexity of the movement.
And yeah, it's good. Okay, I think we should say.
Okay.
I must return to my task of writing this.
Okay. Thank you, sir.
Review. And then next week, I assume we will meet again. I think Garrett's subject at least will be available next week. He thought he would. Once he's settled in Mexico, I think.
Yes. Okay. Okay. Then we see next week.
So maybe we.
Thanks a lot.